Good morning. I'm Tim Irvin. I want to welcome you to the Design Challenge. I'm the director of Texas Space Grant, and with me in the back is College-CyFair, program manager, and up on my left, Nina Martinez is our communications expert. We are now live on YouTube, so if you would like to forward that link to anybody, or have them search for Design Challenge online on YouTube, they can watch all the teams. So welcome. I'm glad everybody is here, all the teams, all the family members as well, faculty, NASA mentors, and other educators that are here to watch all the teams. We're going to have a fantastic morning. Every team has 10 minutes to present, and then up to 5 minutes for questions and answers. I'll be sitting in the side over there. If you have gone to 8 minutes, I'll stand up. That'll just be your 2-minute warning. Then you can wrap up by 10 minutes. We'll take questions from the audience. There is this mic as well as 2 roaming mics if you'd like to pass it around or walk around. Again, the camera is going to be on your left. So the best place for people to stand is between the podium and that first coaster. And if you go outside of this area, you might not be on screen. Just a cautionary tale. All right, any questions before we get started? All right, these are our morning teams. We're going to have 3 groups of 4 with short breaks between them if we don't have too much delay between. And I'll introduce each team. They'll come on up, do their presentation. That'll be presented live again. And we'll go on from there. All right, that lighting's good. Thank you. Is it good on camera? All right, we are good to go. All right, good morning. Welcome. We have our first team coming up. It is Texas State and the Schrodinger's Bobcats.
Good morning, everyone. My name is Logan Swayze, and this is Ian Doge and Zach Parker, and we are Schrodinger Bobcats. Our project is an integrated camera and lighting system for a lunar surface rover, and our approach to this task was to create an autonomous system which controls the lighting array by image data taken from a camera. Some of the context for this project is that NASA missions involving rover exploration will require artificial lighting, both for safe navigation in addition to recording exploratory data for viewing later. Some of the key design constraints that we've taken into consideration for this project was to ensure that our device can be statically mounted to combat the lunar dust problem, in addition to ensuring that our system is autonomous to allow the rover operator to focus on mission-critical tasks. Some of the key features in our design is our image processing algorithm, which takes image data from the scene to extract lighting information from the environment that is then used to control our array of spotlights. Our dynamic lighting array includes this array of 4 spotlights, in addition to a floodlight bank, which is controlled by a manual switch. Additionally, our high dynamic range camera records high-quality images in a dynamic lighting environment.
I'm going to cover some of the changes that we've made from the last showcase. We decided to upgrade from a Raspberry Pi 4 to a Raspberry Pi 5 to increase our processing speeds. We also fully implemented a mechanical subsystem, including a light bar that had mounting points for all of our lights. And then we finished our PCB design of all of our spotlight drivers, which led to us having a full system integration with all of our subsystems connected.
The first subsystem is the lighting sampling camera, and this will take the scene images for the image processing and send them to the Raspberry Pi. The camera has a resolution of 720p and will be taking snapshots at 7 frames per second. Next, we have the HDR video camera subsystem, and this utilizes the Raspberry Pi camera module 3 to capture HDR video. This video is saved on a 256 gigabyte mini SD card, and then it has a maximum video length of approximately 84.6 hours. The camera has an output resolution of 3 megapixels at 30 FPS in HDR mode and has a diagonal FOV of 75 degrees.
Our image processing algorithm is the mechanism which controls our array of spotlights. As you can see here, we have divided up into 4 quadrants corresponding to our 4 spotlights. The way the subsystem works is by taking a snapshot from our lighting sampling camera, converting the image to the HSV color space where the B channel is then isolated to extract brightness information from the image. We then take a ratio of dark to bright pixels in each quadrant and update our lighting array corresponding to that data that we've gathered. And right here you can see an image of the Apollo 15 moon landing as our pre-processing image. And on the right side, we have here all the shadows highlighted with black pixels, as well as the ratio of dark to bright pixels.
I'm going to cover one of the problems that we faced in the design of this project. Digital signals, such as the output signals of the GPIO pins on a Raspberry Pi, are typically driven through pulse width modulation. Images captured abilities driven by this type of signal show a Moira effect, which greatly reduces the quality of the image. You can see an example of this in the image in the bottom right. To remove this effect, our system drives the lighting array linearly through digital analog converters. You'll see a video of this in the video in the top right. Next, I'm going to cover our drive electronics. This subsystem is a voltage-controlled current source that takes a voltage input from an analog source controlled by the Raspberry Pi. This subsystem is duplicated 4 times with each circuit attached to its own LED. The output of this circuit is autonomously based off of the image processing code. Now I'm going to show you a timeline of our drive electronics. On the left, you can see our original design, which ended up having a problem where we couldn't drive our circuit to ground. We then updated our schematic and eventually had a fully implemented PCB. Lastly, I'm going to cover power. We have a dynamic power consumption from our spotlights ranging from 2 to 100 watts. Our floodlight bank draws 144 watts. Our Raspberry Pi 5 draws between 2 and 10 watts depending on whether or not it's idle or if it's stressed, which leads to a max total power consumption of 254 watts.
Some future plans for this project could include a heads-up display for the HDR camera, including hazard detection, and a graphical user interface with remote device control.
All right. Lastly, we'd like to give a very special thanks to Dr. Tim Irvin, as well as the rest of the Texas State Space Grant Design Challenge staff, as well as our NASA sponsor, Ms. Sony Clark, and our Texas State faculty, Dr. Rich Compow, Mr. Mark Walker, and Dr. Jeff Stevens. And then, any questions or comments?
Just to give you an opportunity to talk about it.
Yes.
You did a lot of software programming on this system, and I want you to talk a little bit about, if you have time, about the graphics processing that you did to try to interpret the data from the camera to drive lights.
Yeah, of course, I'd love to. So we're using OpenCV in Python on our Raspberry Pi 5. And the way this algorithm works is we take in that data, we have an original RGB image, we use the OpenCV library to convert this to HSV color space. We're then able to isolate the B channel there, and we have a series of mathematical calculations that are hard-coded into the algorithm to take a ratio of the dark to bright pixels in each quadrant. After that, we do a SPI protocol transmission to our digital to analog converters in the drive electronics, which will then update the brightness of the spotlights. Thank you.
optical, taking into account the optical challenge, like I could go works.
Yes. On the moon, we have incredibly dark regions as well as incredibly bright regions, as I'm sure everyone is aware. The optical challenge that we encounter here is contrast with image data, and so our spotlight array is used in order to create a better lighting environment for our high dynamic range camera, which is again optimized to take images in this dynamic lighting environment.
That's kind of leading on that took on that. So, because that's the true challenge, some of the software you just mentioned specifically designed for challenging contrast ratios.
Yes, so the V channel in HSV corresponds to the intensity of each pixel. So we're able to identify like low contrast regions of the image.
And the last real quick thing, why did you go H.264 and MP4 just the same memory?
So the Raspberry Pi camera module 3, the library that we're using, it encodes in H.264 natively, and so we have to record in H.264 and then convert to MP4 afterwards. H.264 is not supported as ubiquitously on a lot of different systems. So MP4 file is just so we can transfer it between system to system and kind of ensure replayability. No, so we tested a comparison of the H.264 to the MP4 images, and we had very little loss. Of course, thank you.
Any other questions? All right, thank you, speakers.
Thank you.
Audio's good. You want me to move microphones to questions? Or, yeah. Okay. All right. Next up, from University of Houston Clear Lake, we have Team Astro Apollo.
Good morning, everyone. We are Team Astro Apollo. Our project was to develop a softgoods attachment device. Our team consists of myself, I'm Julio Pinzon. I'm here with Lamar Torres, with Gabriel Salazar, and Alberto León. And to give a bit of an overview of our presentation, we'll go over the project background and the goal summary. And then Gil is going to go over the criteria and constraints, the course and standard that we followed, and for our quality. And then Alberto will cover our preliminary concept and the Astro attached external and internal design, which is our final design. And then Gabriel is going to go over the modeling and analysis and the technical content. And then I'll close it up briefly talking about our project work plan. All right, so what are softgoods? Softgoods are high strength, lightweight, flexible fabrics that can withstand high extreme temperatures. They're very important because they provide protection to astronauts and the spacecraft structures during missions. And they provide thermal insulation and protection for against degrees for a lot of the sensitive components. And some examples for applications include spacesuits, inflatable habitats, and airbags. So our goal is to design a tool or a set of tools capable of attaching overlapping pieces of softgoods while only accessing the other facing side, since astronauts cannot reach from behind or under, and So our team's goal was to prototype a reliable and easy to use device, keeping in mind that astronauts have limited mobility and movement in their spacesuits. So now I'll pass it on to Gil to cover the criterion constraints.
For criteria, the total amount of tools should, the maximum amount of tools allowed is 3, and this limits this reduces the weight and also the maximum mass of the tool should not exceed 10 pounds on Earth's gravity. This reduces weight and complexity of the design, and this total device must fit within a volume of 12 inch by 12 inch by 12 inch, and the tool must be manually powered. There will not be motors or electronics device involved. The power can either be linear or rotational. The device and all their components must sink in water or either be usually boiling water. Last, the safety factor should pass 2 for ultimate stress. Several constraints we have is budget. Depending on the budget, we'll have to pick a right material for the MBL material list, and this can save on costs. Next is the limited available manufacturing equipment we have on campus. Depending on the equipment, we might have to do 3D printing or to save on the cost for testing. Next is the ergonomics. It should be simple, easy to handle for astronauts in gloved hands. Because the ergonomics, this can shape the overall structure of the device, since you don't want bulky or hard to handle tools. Next is the tether point. The tether point needs to be a 1-inch diameter. This can also affect the overall design, since depending on where you put it, it might interfere with the structure or integrity of the device. These are some codes and standards. The first code is NASA standard 5002, and it deals with materials such as aluminum alloy. This is for the housing for the device. Second, the standard for 5010. This outlines the requirement for tools to ensure that they're safe and reliable in space applications. The last standard is NASA standard 6001. Focus on the materials so that they can pass the requirements and process to withstand harsh conditions in space. Depending on the key requirements and constraints, we use a house equality to determine which concept was best. And concept 2 outperformed concept 1 in areas such as low maintenance, reliability, and how safe it is to use. I'll be passing it down to Alberto.
Thank you, Gil. So to begin, our preliminary concept design was modeled at the beginning of our brainstorming process. It was modeled after a conventional fabric stapler with grippers on both ends to grab the soft good and attach it with a unified handle that operated the grippers through an internal spring linkage system. The grips were internally connected that way. However, once we received more information over the competition and we had some of our questions answered, we decided to develop our final concept design, which was the Astro attach, which builds off of concept 1 with modifications for enhanced stability with a wider grip area for the astronaut to be able to grab it with their EVA gloves. Also, it was an enlarged grip. Central grip features a stippled texture and ridges placed on the backside for a non-slip environment for comfortable handling. Next, we have our internal design, which consists of 7 components made of stainless steel. This consists of a sear, a spring, a driver beam, a grommet, a staple driver, and cartridge. The way this works is at the heart of the device is a driver beam, which is pulled back by simply actuating the handle. The beam is connected to the staple driver, which is linked to the sear mechanism. When the sear is disengaged, it releases the staple driver, dispensing a 1/2-inch staple to attach the soft goods. The dimensions of our device are 11 inches in length, 8.3 inches in height, and 2 inches in width. made of 2024 T4 aluminum due to its high strength to weight ratio. And as you can see, our tether point is attached on the grip, so the astronaut can attach it to their suits to make sure it doesn't fall or anything. And now we'll pass it on to Gabriel, who will be speaking about our modeling and analysis.
So FEA was performed on the angle to, because this was most likely the component that was going to fail. One of the requirements is that it had to withstand 20-pound force, so 20 pounds of force. So the CRM is fixed to simulate a worst case scenario. So when the FEA was ran, that the max stress came out to be about 21,000 psi, and the yield strength of 2024 aluminum was about 47,000 psi. So the factor of safety came out to about 2.3. This table shows some criteria and constraints and technical content of how it matches that. So the maximum of tools that we were allowed to have was 3 with the Astro attach, so just 1 tool. The maximum weight was also 10 pounds. The Astro attach came up to 6. Max volume was 12 by 12 by 12, and the Astro attach came out to 11 inches by 8.3 inches by 2 inches. It also had to be manually operated. This Astro attach is manually operated with a linear mechanism. The materials had to be NBL approved. It also had to sink. So it had to sink in water. So that's one of the reasons why aluminum was chosen. And I also had a tether point. And the Astro attach has 1 tether point. I'm going to pass it on to Julio to go over our project work plan.
Alright, so here's our work breakdown structure, and we used to keep track of every task that we needed to complete to stay in charge of the project. As of today, we completed up to task 4.3. And on the next slides, we have our Gantt chart, which also helped us to stay on track with everything that we had to do. And as you can see on the picture up there, the tasks on blue are stuff we have completed already, and the ones on green is things that we have left to complete. All right, thank you for listening to our presentations, and if you have any questions, go ahead. Thank you.
Yes.
How do you plan to test this?
We plan on testing this by first trying to create a 3D printed prototype and buying MLI, something similar to it, to staple through and see how it reacts. See over time the holes on the MLI play a factor into how it degrades and properties. That's our next step in this upcoming semester, is to find a way to develop it and make any final improvements, which there is room for, and do a little bit more research over the MLI material and see where it goes from there. Thank you.
All right, I can run the mic for questions.
Go back to your graphic, please. I'm trying to understand how I think your intent is to put a layer on top. A layer on top of a resisting layer, but I'm not sure how you do that. To pinch the two together.
Was it that one?
Well, go to the tool. How would I pinch, say, the layer you want to add on top to the underneath layer?
The tool. What was your question again, sir?
How do you get your top layer you want to add to the lower layer? I mean, how does the machine grab the two, or I'm pinching together?
Okay. So essentially, from what was provided from competition, is to design a device that once the astronaut, the problem we're tackling here is on the space station when they use softgoods to cover existing structures. So when they have to do maintenance on these structures, what they do is they cut out the softgood. So they need a device that would be able to patch it up and attach the softgood back on once they're done with repairs. So the way it would work is the astronaut would, once they cut out the socket, they would lay it over again, the original spot it was on, and staple it on. That's the way we designed the device.
It's like a state.
Yes, sir.
Other questions?
Regarding the staple itself, since you can't access the backside and there's likely no hard surface on the backside of the soft good, how is the staple going to actually fasten the soft good, the new soft goods level soft good?
Just the friction of the staple itself holding onto the soft good, the pressure.
Any other questions?
Is this tool also supposed to be applied in the lunar surface, or is this just for the axis?
So just for microgravity.
Okay. And then the other question I had is the tool designed to accommodate different size blocks. If you look at the full control from the trailer.
We just had one generic size in mind, just a bulky glove, but not different sizes.
Any other questions?
So I see that the gun or the staple gun is 11 inches in length. I feel like the trigger is going to be too far away from the actual handle to pull the trigger, I think, because the astronauts don't have a lot of dexterity in their fingers. There's just not a lot of mobility. So am I wrong, or do y'all have like a solution, or do y'all think like it's good enough for them to work?
We developed this, and like I said, there is room for there is room for improvement. We are open to any feedback, so that is one thing we're considering. We did try to make it curved just to be more comfortable for the astronaut to use, but the point you made, it is a great point. So it's something that we plan on improving. Especially once we start printing it out, to see how it feels in hand and see what adjustments we could make. So thank you for bringing that up. That's a great point.
Thank you.
All right, thank you, team. All right. Next up, from Prairie View A&M University, the Astropanthers.
Hello, I'm Warshak the Fourth.
I'm Jacinto.
I'm Noah Crew. I'm Percy Grady.
I'm Christopher Moore, and this is our presentation on the Lunar washer and dryer combo. So currently, astronauts have to wear clothes until they're no longer usable. This is because of no way to wash them in space. So typically, once the clothing is too soiled or too worn out, it is packaged and put into cargo ships, which upon re-entry are burned up in the Earth's atmosphere. While this is an effective way for waste management, it requires that large amounts of clothing be brought during the
emissions. This adds significant weight and takes up valuable storage space. To address the concerns of waste management and the amount of clothing brought on emissions, our team has embarked on a journey to develop a enhanced washer and dryer combination. This machine is tailored to is based off of Earth-based models and tailored to work in the unique environments that space provides. Our machine is conditioned to work in low power, low water, and low gravity environments. This will provide a way for clothing to be washed, reducing unnecessary weight and increasing the sustainability and feasibility of long duration missions.
Okay, so the design constraints for this design. First, it needed to be derived from current washer dryer technology, the all-in-one technology, and we emphasized the efficiency with water usage, power consumption, and time to launder. We also needed to operate at an atmospheric pressure of 70 kilopascals and operate at lunar gravity, which is 1/6 of Earth gravity. And we needed it to, we designed it to be minimally intrusive to the cabin already. And we had to minimize the size of the machine, and the clothes must not come out damp.
We had 6 design requirements. The first was to employ evacuated pumps, seals, and valves, and use sealed pressure compartments. We also wanted to include a horizontal tumbler for the drying phase of the combo, and we want to integrate an energy recovery system to cycle waste heat from the drying phase and plan operations around peak power availability, just to reduce the number or the total amount of power usage. We also want to have fail-safe systems and provide a safety valve, safety valves that automatically regulate pressure. Both requirements 1 and 4 were to decrease likelihood of heated air from escaping the combo. We also want to include dust-proof enclosures for internal components, filtration systems, and airlocks, so we can increase the lifetime of the combo. And lastly, we want to include thermal control systems such as heat sinks, phase change materials, and radiators for controlling heat rejection and to avoid overheating.
So for our design, we designed it based off of the GE's profile washer heat pump dryer combination machine. The outer shell material should be made out of plastic. This is to help save on weight concerns as well as have a solid piece of material. The outer shell dimensions are a length of around 60 centimeters, a width of around 55 centimeters, and a height of around 90 centimeters. This gives us a total volume of the machine of around 0.3 meters cubed. This is about half the size of a normal heat pump washer dryer combination machine, which is around 0.665 meters cubed. The drum material is an aluminized alloy that serves 2 major functions. This is to save on weight as compared to something like a stainless steel alloy, and then it also helps with rust prevention. The drum dimension is around a radius of around 25 centimeters, a length of around 50 centimeters, and a wall thickness of around 2 millimeters. So for the functionality of the washer portions of the machine, it is very similar to terrestrial front load washers in terms of there's a tumbling motion that will wash the clothes, essentially serving similar to what an agitator does in a top load washer dryer system. This allows the clothes to be tumbled and washed because of that. So the major changes that we made, we created a longer soaking period, or planning a longer soaking period for the clothes to be washed when being washed. This serves 2 major functions. It allows the water to have more time to penetrate the fabrics, and allows for the dust particles to be further separated from the clothing. And it allows for a period of time for the machinery to cool down and not be working as hard for an extended period of time, especially working at lower pressures. There's a good chance of overheating. We also sort of mostly eliminated the rinse portion of the machine. We are limited to around 20 kilograms of water for each cycle, which is a lot less than terrestrial models. And so to eliminate this, we use a very fast spin cycle, which helps remove all the dust and particulates while eliminating water at the same time to make the drying cycle easier. So for a couple calculations we made according for the washer, we calculated based on the rotational energy, we found the moment of inertia with the washer drum, as well as the close within the machine, and then we used that to determine the maximum angular velocity we could achieve, which is around 610 rotations per minute, using around 600 joules of power.
For the operations of our dryer combo, the dryer portion of our combo. So initially, it will be forced through a heating element on the right side of the image. Then that will be pushed into the drum of the washer, and then that hot air will evaporate a portion of the moisture within the clothes, and it will be removed from the dryer to the exit. Then once it's out of the dryer drum, it will be forced through the condenser, and then that condenser will remove some of the moisture within the air, and then that air will be forced back through the heating element, and then that cycle will continue until the clothes are completely dry. And the water taken out of the clothes is going to be stored within a container within the washer dryer complex. And one of the adjustments we had to make this work in lunar gravity is to reduce the RPM of the dryer cycle, because typically in a terrestrial washer dryer or dryer cycle, if we had that same exact rotational speed, the clothes would just be stuck to the edges of the dryer throughout the whole cycle and not allow them to tumble, which significantly reduces the time for a dryer cycle. Here's some of the equations we use to determine the rotational speed of the dryer. So initially we had to solve for the angular velocity of a terrestrial washer dryer or a dryer cycle. And then we used that to determine the acceleration, and then found the ratio between that and the gravity on Earth. And then we just multiplied that ratio by the lunar gravity to find the centrifugal acceleration that we needed for the lunar dryer cycle, and then we used that to determine the angular velocity that we would need for the dryer cycle.
So future plans for the design are to incorporate the wiring and logistics for the physical model. And also for the physical model, we plan to include analog switches and buttons. And we also plan to consider the integration to pre-existing cabin systems. And we need to create code for the different cycles.
Thank you. Any questions?
So I have a question. So dealing with ultimate gravity or lower gravity or even microgravity, some of the most complicated systems on ISS is the space body and the water dispenser. And part of that is the management of fluid at a lower level if you know reduce gravity. So how did in your design how did you address the difference in the motion of water?
So we were still doing a lot of research into that. We're all quite young, and so we're learning more about like fluid mechanics and how those are affected by gravity. But essentially, the major changes were the slower spin speed. So we know that the water won't move as fast, like accelerating downward while doing like tumbling actions. So using a much lower spin speed as compared to normal washer dryers here on Earth was the main sort of change that we made. We wanted to look a little bit more later into like the washer pumping systems and draining systems to like really go into and delve into the process as part of our future plans.
I have two questions for you. The first one will be, you talked about water being going down to storage tank. How do you plan to filter that water? You guys looked at that design, how do you plan to filter it out due to the lunar dust that will be inside the habitat mentioned over time and duration. Second question would be, what are you looking at for your maintenance program on this? Because getting parts to the moon is not easy.
Yeah, so first, your first question was about the water recycling system, correct? That was part of our future plans. We were going to look more into that, having some sort of local recycling or filtering system within the machine. We were trying to look and see if that was possible. We don't know if we would be able to fit all of those parts inside of the machine, so possibly in the pipe draining it, and that would go to the water reservoir for the entire cabin is where we would look at sort of creating that recycling system to filter out any sort of detergents left or lunar dust, as you mentioned. As far as what was your second, the maintenance program, right? So for that, we wanted to look into just like bringing a couple extra like motors and different things. So these motors shouldn't weigh too much. We were planning to use around a 700-watt motor, which isn't terribly big. So bringing in maybe an extra two motors like onto the mission in the first place, I believe would make a lot of sense regarding that. And then the machine will be located inside the cabin, which will allow for the astronauts that are on the mission to be able to do maintenance in that sense.
Thank you very much, team. All right, please welcome the Cosmic Javelinas from Texas A&M Kingsville.
Hello everyone, we are the Cosmic Javelinas from Texas A&M University Kingsville. My name is Marco Antonio Hernandez Jr. I'm the team lead for our group. This is Kevin, Ryan, Mark, Angelina, and Emilio. We are going to cover our human exploration rover. This is for a challenge, a competition.
The topic we chose for TSGC was the Human Exploration Rover Challenge competition, otherwise known as HERC. This engages students in hands-on design, which relates to the NASA missions, and it aligns with the ABET college criteria. Our team will be participating in the HPV division, which stands for Human Powered Vehicle. This challenges teams to design and build a human-powered rover to overcome diverse terrains.
So there's 10 obstacles in the Human Exploration Rover Challenge, and to simplify our design process, we decided to split them up into 4 groups, with the first group being obstacles 1 and 2, and they pretty much consist of just rocky terrain with alternating terrain elevations, essentially trying to make a rover geotoggle. And the second group, which consists of obstacles 3, 4, and 5, are essentially the ramp portion of the course, which just consists of ascending and descending ramps, with the one in the figure being obstacle 4, which is essentially a 30-foot long, 5-foot high, 30-degree incline ramp, which is also a constraint which we'll get into in a bit. And for the third group, which only consists of one obstacle, which is obstacle 7, and that's because it's the only one that relies heavily on our steering capability. And if you hit one of those nicknamed ice geysers, then you're automatically out of competition as well. And for the third group, which consists of obstacles 6, 8, 9, and 10, is essentially just 4 different types of boxes that are filled with different types of materials, with the one shown in figure 4 being a more gravel/pebble-like terrain.
The main objective is to construct a human-powered rover to complete the 1.5 mile long course and all 10 obstacles in under 8 minutes. Some milestones we'd like to achieve are having our total weight of our rover under 130 pounds. The turning radius of the rover has to be under 10 feet. The braking system has to hold drivers on a 30-degree incline. We need to have a ground clearance of 12 inches, and the maximum dimensions of our rover is 5 feet in length, width, and height.
So here are a few of our main safety features. The main one is going to be a 3-point harness for each driver that will keep us each secure. Lower center of gravity that will help us on the tilt and the ramps from tipping over. Reclined bucket seat design that will keep us more supported. No rough or sharp edges on the frame and the seats itself. And all of our welds will be performed by certified and master welders.
So to initiate a more in-depth design process, our team formulated a design matrix. And so we separated the rover out into 6 components to help with our design process, and it's consisting of our frame, our drivetrain, the suspension, the steering mechanism, the seat, and the suspension. Steering mechanism or the drivetrain is not listed here because at this point in time we haven't formulated a design for it yet. But the highlighted choices are what we ultimately went with regarding the frame, material, suspension, seat, and wheels. And this was our first mock-up sketch. And we initially went with a general square frame design because it's generally average in structural strength. And we knew from the beginning that double wishbone design was going to be our top suspension choice only because it's various applications and different types of motorsports. And it just decided to fit our needs from the beginning.
So this is our initial concept. This is to give us a baseline of something to build upon as we progress with the CADs and what research has been done. Currently, it has 20-inch diameter wheels. We have the one with the I-frame. It has 12-inch axles with the big seats on its backwards so that we have a lower center of gravity. And this is the second concept. So in this one, we had the drivers measured for the seating. So these are at the measurements of the drivers. The control arms were added. And the axles were shortened. We chose a wheel design of 3 swirls or spirals.
These are our rover features that we needed to implement within our design. So turning radius less than 10 feet is required by the HERC handbook. Indirect steering is something we chose for maneuverability, and Ackermann geometry is used to help with our turning radius, which we will get into later. We have a double wishbone suspension setup, a reverse gear for the rear seats, so the person can pedal in the direction they're facing instead of having to pedal backwards to rotate the tires, and angle bump seats.
So the capital R represents the front turning radius, the lowercase r represents the rear turning radius. As you can see in the slides above, we have 7 cases in total, 1 special case and 6 acceptable cases. The 1 special case includes a front tuning radius of 10 feet and above, the rear tuning radius of 9 feet, no, 9 feet in total. So it'll only be chosen if all the other acceptable cases aren't usable. However, the 6 acceptable cases that are usable will be determined on how sharp the team wants us to turn it.
So this is indirect steering. This is where 2 tie rods are connected to a spindle located at a pivot underneath the driver's positioning. And the handlebars are connected to that pivot, which will allow a decrease for our turning radius.
Okay, for the Ackerman steering, we have regular, which is it'll cause slippage on one wheel and it'll have strain on the other, and it'll cause misalignment on the front and rear travel paths. But for the Ackerman, we have our gyros accommodating for no slippage, as well as having a sharp turn on one wheel, but having it more subtle on the other. This will help align both the front and rear wheels travel paths.
Due to the undulating terrain that is current in 3 of our obstacles, we chose double wishbone suspension, as it allows us to have one wheel move independently without affecting all of the other wheels.
For these calculations, we had already predetermined our gear ratio, our rotational speed, and our torque output. All we needed to determine was our torque input and our rotational speed input as well.
Here's our current seat design. We chose aluminum 6061 alloy just for its properties. For both seats, the total mass would be 18.8 pounds, and some of our key features would be we added poles to reduce the weight and increase the radius to ensure that there's no sharp edges and 3-point harnesses.
This is our current design. This is with all the other slides added on. So we have the new seats, we have new suspension, and the frame was modified to allow the suspension to have more travel. This wheels were slightly reduced. We also added gears and pedals, and the handles were the same.
This is our finite element analysis for our current rover design. We have shown our displacement and our stress distribution graphs. And we have fixed points set with control arms and frame beams. We have 155 pounds on the front seat and 190 pounds on the rear seat, so the weight of our drivers. And we have 200 pounds of force on the backs of the seats and 250 pounds of force on the pole of the pedals, or where it's welded onto the frame. Then when you're pedaling, you're going to be pushing against that wheel.
In conclusion, we are at a technical readiness level of 3, so we're still in development stages. We're testing, we're doing simulations. We achieved a majority of our goals, so keeping our weight under 130 pounds. Our current weight is around 90 pounds and from SolidWorks, so we still have a lot of wiggle room. Still need to implement things such as brakes, and we have a training radius under 10 feet and a 12-inch ground clearance. And for future plans, we're on track to start building late January, early February. We're still improving some of our designs, making sure they work, simulating a lot of things. And welding is going to be our toughest obstacle because it is aluminum. A lot of special gases are needed for aluminum, but we have certified welders to help us. These are some of our references. And do we have any questions from anyone?
Questions?
Is your setup for one driver to provide forward motion and the other reverse, or is there gearing where both can
contribute to forward motion?
Both of the drivers would contribute to forward motion. So the driver in the back would pedal forward, but we would have the gearing that would allow the person in the back to go backwards, which would pitch forward the person in front.
I have a question, guys, for the tripod, I didn't know, like, when it comes to turning steering though, uh, how much they can steer, like, is it hard to steer or is it easy though?
The indirect steering is arguably the best choice of steering for this type of design. It's similar to like recumbent trikes, if you're familiar with those. So it's because you're sitting down that the steering mechanisms with the tie rod setup, you don't have to go with the direct friction of actually turning the tires, which you have to do with direct steering. So it's easier for you to choose.
You said you guys plan to do brakes, or y'all thinking like cable brakes, hydraulic brakes, and just like front and rear, and also discs, or what's your plan? There's a lot of angles for that.
So for brakes, we plan on going for wired brakes, just because we believe it would be easier and more responsive for what we need.
So you're just gonna put handles on the front, so only one person has access to the brakes, and then you're gonna have brakes in front and back, or you still work on that?
We're discussing that because we could give the person in the back brakes, but that would have to, the person in the back would have to actually communicate with the person in the front. So we might just stick with the person in the front, just having the brakes on the handles.
All right, thank you, team.
They're just putting motion to this back side.
All right, now we have a quick break until 9:45. If the next two teams presenting could make sure you have your presentations appear on the laptop, or let me know if you're going to swap laptops. Please welcome the Artemis Owls from Rice University.
Good morning, everyone. Thank you all for being here. As mentioned by Dr. Tim Urban, we are the Artemis Owls from Rice University, and we will be presenting our lunar rescue concept for incapacitated EVA crew. I am Laro Castillo.
I'm Captain.
I'm Aga. I'm Mac. And our final team member, Favorite, he could not be here today, unfortunately, but he's also part of this team. And here are our mentors. We have Ms. Vaughn, who served as our NASA mentor. And we also have Dr. Trevas and Dr. Woods, who serve as our Rice University mentors for this project. So in this presentation, we'll be covering a general background, pretty much the situation at hand and why we have a desire for this product in the first place. We'll then go into details about our design concept and cover all the features that we have implemented into our design. We will then go into the rescue process, which is how we see our design being used in the first place. And we'll wrap it up with next steps, what we plan on doing to refine and improve our design for the next semester.
Can you hear me? Hello. So first up is the project background. So this device is going to be used for the upcoming Artemis 3 mission. It's our return to the lunar surface. In this case, we'll have teams of 2 astronauts conducting extravehicular activity, or EVAs, on the moon. And we're thinking about the situation where, what if one crew member becomes incapacitated or becomes an ICM during these missions? So to summarize our concept in the mission statement, we set out to design a lightweight and compact device that can safely rescue and transport an ICM during these EVA missions.
When designing our solution, we have to focus on 4 main objectives. The first being minimization of resources, so that includes mass, power, and volume demands. Portability, an EVA can last up to 8 hours, so the solution needs to be easily brought along throughout the entirety of that mission. Ease of deployment, when a crew member becomes incapacitated, the survival of that crew member is on the clock, so we need to be able to deploy as quickly as possible. And lastly, ergonomic. The astronaut suits have very limited hand dexterity and suit mobility, so the solution should not require any extensive body movement or fine motor skills. When designing our solution, we also have to consider a lot of different constraints. First and foremost, and most importantly, to preserve the health of the incapacitated crew member throughout the transport back. We also have to support their weight well, able to withstand the extreme cold temperatures of the south pole of the moon. It should also be able to traverse inclines of up to 20 degrees and cover at least 1 kilometer. And lastly, be tolerant to the microscopic dust on the lunar surface.
With this design criteria in mind, this is the design concept that we developed. So the first part of our design concept is a platform for the ICM to rest on, which consists of a cavity designated for the ICM's life support system. The platform's height can also be adjusted according to the varying crew members' heights, as well as for full compactability inside the lunar vehicle. And the platform can also be steered with motor-assisted wheels on the front to assist with traversing the lunar terrain. The second part of our concept is a tripod stand, which is attached to the platform throughout the EVA mission, but can be deployed by the healthy crew member in the event that their partner becomes incapacitated. And this allows the healthy crew member to mechanically lift their partner off the ground versus just manually lifting.
So next we'll go into some details in our current design. So first we'll focus on the tripod. Here for the tripod, we have a lightweight, compactable, and foldable design that is really easy for astronauts to carry on EVAs. Once unfolded, the tripod stands at a height of 5 feet, and unfolding exposes a manual winch in the middle, which provides significant mechanical advantage to make it much easier for the healthy crew member to lift an incapacitated crew member lying on the lunar surface. In addition, at the bottom of each of our tripod legs, we have developed a traction service so that the tripod does not slip during operation.
Focusing on our next subsystem here, the actual ICM support platform. So I want to focus here on first this platform that's made very, very sparse, very lightweight. in order to minimize mass and volume as usual. This platform also features a wheelbase that allows for connection with suspension, which is one of our future endeavors we'll take on next semester. We also have currently here in the back housing for the lead screws, which we'll use to raise and lower our platform, as well as some extra supporting bars for the life support system. And on the handlebar, we'll have an interface with some pressure sensors or some sort of tactile interface that allows both the wheels to be driven and for the lead screws to be driven to raise and lower that platform height.
To raise and lower the platform, we are using a Scott-Russell linkage mechanism, which is operated by a lead screw, which is operated by a motorized lead screw, which converts the linear motion of the collar into the angular motion of the platform. For this design specifically, our inclined angle is between 0 to 36 degrees. 0 degrees for full compactability inside the lunar lander vehicle, and 36 degrees to account for the tallest crew member height.
As Max said, to assist in the transport of the incapacitated crew member, we elected to add direct drive motors to the front wheels. We hope this is able to reduce transport loads significantly and also assist in going up inclines. To drive the motors, we decided at this point to have hand pressure sensors to accommodate for the limited dexterity of their gloves. And we built our first prototype with an Arduino microcontroller just to conceptualize this functionality.
Now we'll talk about how we plan for our design to be used in case crew rescue is needed. So in our scenario, we have a pair of astronauts going away from the home base on some mission they need to complete, right? And one astronaut is going to be pushing the platform with the tripod attached to it. And once they're out there working in the field, in the event that one of the crew members suffers an injury or a medical emergency, once a healthy crew member notices them, they'll go back to the platform, unclip the tripod, and bring it over the incapacitated crew member. And they'll place it over the attachment points on the spacesuit of the ICM. And once they do that, they can take the rope from the winch and hook it onto the attachment points of the spacesuit. And then once the rope is all hooked up, the healthy can start cranking on the winch in order to slowly hoist the incapacitated crew member up from the lunar surface. At this point, the incapacitated crew member will be at a position where their heels are on the ground and their body is at a slight angle from the lunar surface. And we designed the winch so that if there's no motion going on, there's no cranking going on, the winch is locked in place. So the incapacitated crew member will not fall from this position, the rope will not let go. So now the healthy crew member is free to go back to the platform and then push it and maneuver it so that it's under the incapacitated crew member. Once that's done, they can go back to the tripod. They can crank the winch to slowly lower the incapacitated crew member onto the platform. Once the ICM is settled on the platform, then we can unhook the rope from the attachment points on the spacesuit, fold up the tripod, and pull it back over the platform. Now the healthy crew member is free to push the ICM back to home base for treatment.
All right, and for our next steps for this upcoming semester, we have planned to look into a more footable platform so we can ensure there's minimal volume when the product is not being used. We also wish to look more deeply into the wheel assembly. This includes both the suspension and also the wheel design itself, so we can optimize it to be better suited for the task at hand. We're also looking into how we can incorporate a better use for multi-use for our product. So in the event that there is no need to rescue an incapacitated crew member, how can we make sure the device is still being useful for the two crew members on their missions? We also wish to look into an automatic braking system to add this as an extra precautionary feature so we can make sure that our device is as safe as possible. And as for all the electrical equipment, we're looking into a thermal management system to ensure they are still operable within the extremely cold temperatures on the moon. And finally, we also look into material selection, so we can look into more aerospace grade materials, run some finite element analyses on these, and make sure they are able to withstand the conditions to which we are exposing them. And lastly, we'd like to give some thanks and acknowledgements to our mentors, Ms. Vaughn with NASA, our two Rice University professors, Dr. Trevis, Dr. Woods, and of course, the entire team here at Texas Space Grant Consortium. Thank you. We will not take any questions.
So you mentioned that you were using a motor-assisted wheels on the system. Did you do a trade to look at what if you really needed to use motors? Because that is something that's a part that could have a failure, could get ground up by a regulage, and there are other mechanical means instead of using a motor.
Yeah, that is something certainly a consideration that we took heavily. We did a lot of decision matrices between systems that didn't require motor systems and systems that would just be mechanical. And we decided that because the life of a human here is at stake, our first priority is to be able to get the person back as quickly and safely as possible. And so at this point, we feel that the motor system provides enough advantages to necessitate the use of the motor system at this point. But there are further analyses and research to be made in the next semester that can justify that.
What we didn't mention that we wanted to pursue next semester was some notion of freewheeling, so that the car can be pushed without being restricted to the motor. So we're looking into that. So just in case of failure of the motor, or even if the astronaut opts to not use the motor, we're looking into options to allow the car to be pushed, to allow the wheel to move independently from the motor when the motor is not activated.
So I wanted to ask you a question. You developed a tripod for a winch. Two questions that come from that. One, where do you plan to attach that winch mechanism, which is an astronaut suit, which is lunar suit? Current designs of lunar suits do not have an attachment point for such an idea. And two, how is the astronaut planning to attach it when the person is laying on the lunar surface and bending down to that operation? It's very difficult to get up from that operation on their own. How do you plan to tackle those two approaches?
Yeah, it's a good question. So as part of our design problem, we were told that the suit would have attachment points, two at around the shoulders, two at the waist. If that's changed, that's something we can definitely consider and think about other ways to connect. But at the current standing, that's what we were told, so that's the design we went with. And as for the bending down, we have right now the consideration is that's the one time where the healthy pointer would have to bend down and attach at that point. And so we tried to minimize any other sort of bending by allowing the winch to be placed at a 5-foot height, which allows cranking from a standing position, as well as the adjustable handles, which also minimizes having to bend up or down for any reason when pushing the dolly or the platform. And so we've also thought about maybe adding in some way for once you lower that winch down for the connection to be made easier without having to bend down, whether it be using some sort of hooking system that we can sort of swing from like a waist height or something like that. But right now we do just have that one instance of needing to fully bend down to attach those points.
You had mentioned that in rescuing an incapacitated crew member, time is of the essence. And then you also mentioned in your presentation that once the incapacitated astronaut is lifted up, that the able crew member should fold up the tripod, put it back on the sled, let's say, and take it back. Why don't you just leave it behind? Isn't that a waste of time in a life or death situation?
Yeah, so it's definitely going to be a case-by-case basis, depending on the severity of the injury. If it's something like a medical emergency that requires loss of speed, then that's definitely, there's no need to reattach the tripod, so it's definitely something where we can set the tripod up, move the ICM off the platform, and then just get out of there as soon as possible and leave it behind. The idea is that this device is reusable though, and so it can continue to be used for future missions. And so in the case where it's possible, and that's sort of up to the discretion of the healthy crew member, we would also want to have the capability for that tripod to be refolded and reattached so we can, for future missions, maybe not immediately, but in the future, reuse this device with its full functionality.
All right. One more.
Since you have two systems, I was wondering if you have any idea what the total mass might be. Do you have any idea? I know that you have a phase 2 coming up, but.
Yeah. So currently, we've looked into like some of the weight and mass requirements for like the independent system themselves. I believe during some preliminary calculations, we found that the tripod, if we had made the assumption it was being made out of aluminum, being at a height of 5 feet, I believe that by itself came out to be about roughly 60 pounds, I believe it was here on Earth. As for the platform itself, we are still making many considerations for the height of the platform, also the material of the platform. So we still don't have any exact decisions in mind for the weight of the platform.
Okay, and then my second question was, how do you envision the crew member transporting this nominally during their EVA?
Yeah, so currently our plan is for this platform to be pushed during the EVA. That is why we have chosen to try and make this as sparse and as lightweight as possible to make it less of an inconvenience. Since we do have envisioned that for every mission our crew members go on, they will be carrying this device with them. So trying to make this, so I'm trying to also make this, like as lightweight as possible. They can possibly even carry like some tools on the platform when they're first bringing it out onto the missions.
All right. Thank you, team. All right. Next up, we have Lone Star CyFair and Team Aquila.
Hello, everyone. We are Team Aquila from Lone Star College-CyFair. My name is Thomas Johnston, team lead.
Jose Redondo, Dick lead. Caleb Witten, lead engineer.
And Trey.
And our device is a lunar contact sampling device. And it is also worth noting that this is going to function as a class project as well. So, as we're all aware, NASA plans to travel back to the moon on the up-and-coming Artemis 3 mission. On this mission, NASA has a plethora of objectives that they will accomplish, one of which being to collect a sample of lunar regolith in order to study grain orientation and erosion patterns. Our mission is to deliver a device to NASA that they can use for those purposes. As previously stated, the device is going to function to collect samples of regolith for erosion patterns and tectonic movement. And in these images right here, you can see the an example of a desired location that they are going to use the device in. There are some criteria, however, but the most important bit of criteria is that the sample must remain in its natural orientation for an accurate study of tectonic activity on the moon. If the device does not accomplish that, it is essentially null and void. So, some of the other criteria, aside from retaining the orientation, include collecting and storing the top 1 to 5 millimeters of regolith. The device must fit within an 8 by 8 by 16 inch storage space. It must also have no sharp edges, weigh 10 pounds or less on Earth's gravity, use only manual power, and while using manual power, the actuation force cannot exceed 89 newtons or 20 pounds. All of these are per micro G guidelines. I will now pass the mic to Jose so he can discuss our research method.
We looked at the original NASA sampling device used in the Apollo 16 mission, which was used the beta cloth material at the bottom as an adhesion material to place onto the regolith for collection and storage. Although the device was successful in its mission, it did not maintain grain orientation, which is something that we intend to expand upon. And some products that we use for inspiration for our preliminary designs are the snake catcher stick, the cookie cutter, and self-inking stamps. Which leads us to our preliminary designs. The stamp itself, as the name implies, is used as a stamp, where you simply press it down to collect the sample, release it so that the sample goes into the actual storage space. However, the problem was that jamming could occur due to lunar regolith going inside of the machine. Number two, the rego collector is a very simple mechanism based upon the actual cookie cutter, as mentioned in the previous slide. Again, you push it down into the regolith, then slide in a separator sheet to seal off the sample. And the problem with that is that the astronaut would have to bend down to actually collect the sample. And three, the iris, it's a rotary actuation force to actually close the sample and contain it. The base plate, however, was too thick and too wide, making it too hard to actually push down and collect a proper sample from the lunar surface. Which leads us to the design decision. The NASA device was used as our datum, and from the preliminary designs and using the micro-G criteria, we came to the conclusion, as indicated by the Q chart, that design number 2 was our winner. Now, to further explain why, I will pass the mic over to Caleb.
So here in the center of our screen, we have a section view of the rego collector. As you can see, it is the top. The brown area is our collection area. And then we have the gray part, which is our actual cookie cutter. During operation, you will press the rego collector down into the surface, where the regolith will enter through the bottom up into our collection area, compressing this brown foam. You'll then take a separator sheet, inserting it through the top of the device into the horizontal plane where there are grooves, which will guide our separator through the machine to the back, sealing our sample. On the left, we see our concept for our grappling cane, which will hold our box. So that way the astronaut does not have to lean down for every sample that they have to take. I do want to say, so our rego collector is a single sample container. Once you've collected that sample and you've sealed it, you can take that off of the cane, put it in the box, grab an empty box, and move to your next sample area. Here we have a blown out version of our containment box, as well as our grappling cane in its folded and deployed configuration. It looks like we have a lot of sharp edges on our box, but I assure you they have all been rounded out. Our separator sheet, as we have here indicated by our bubble here, we do have points on the end of our separator sheet, so as it rides through the grooves built into the side of the cookie cutter, any regolith that falls into our groove will get pushed back out into the sample or pushed out of the back of the device. And again, like I said, right now, our separator sheet does require the astronaut to bend down and operate it manually. However, we are planning to revise that in the coming semester. During the design evaluation, we ran an FEA analysis. While micro-G requires no more than 20 pounds of force to operate the device, we tested up to 40 pounds or 180 newtons to show that our device will not fail during normal operations. We also ran a displacement test under which over twice the force was used. We only had 0.5 millimeters of displacement on our design. That being said, I'd like to bring Tria to talk about our next part.
So my sheet has 16 total requirements. The on the table, it shows some of our requirements that we have met. For our future plans, in addition, we want to add a handle that is issued to the gloves of the astronaut. We want to redesign the separator so that the astronaut does not have to bend down while operating our device, and adding grip to our clamp, so increase grip, and create a lock mechanism for ease of transport and security. For our manufacturing, the box will be 3D printed out of tough PLA. We will attach the foam towards setting up the lid, and a separator will be made from thin and flexible material. The can will be made of commercially available parts. And for our testing, we will test the prototype using regular stimulate following Microgravity testing guidelines. It will make sure that the sample orientation will be original. I'll pass it on to Thomas.
So, Team Aquila has successfully designed and validated what we believe to be an adequate preliminary design for NASA to use on the up-and-coming mission. We would also like to thank Dr. Wang for her guidance with this project and competition. The same gratitude also extends to those of TSGC, Microgravity, and NEMSA, as well as the Lone Star ASME Club. Another thing that I did want to briefly mention, one of our teammates, as you can see in the image right here, was unfortunately not able to make it here with us today. However, it is worth noting that she was a very active contributor in this project. Her name is Tanya Torres. But back on the topic of STEM outreach. So this slide basically shows two separate pictures where Team Aquila attended the event known as CyFest at Lone Star College-CyFair, which is where families come in and they ask you about different careers, and we set up an engineering table and had guests for about 3 to 4 hours out of the day. And thank you. Now I'm going to open the floor to any questions.
Y'all emphasize that orientation was the key thing. Can you explain that? Is that orientation within the sample itself, or did they really mean like with respect to the moon, you know, like here on Earth, the geologists study, you know, the magnetic, the way it's trapped in the rock, so they know that, you know, 100,000 years ago, the magnetic field flip-flopped. So can you explain what you mean by orientation within the sample itself, or with the way it was on the moon, so they can potentially address magnetic field over the...
So our understanding of the requirement is that however the regolith sits on the moon is how we want to present it on the Earth. So I like to think of it as cookie dough on a cookie sheet. When you take your cookie cutter and you press it into the cookie dough, you have a specific form that dough is in. You can then take it and transport it to your oven, and it'll be in the same exact orientation as when you place that cookie cutter into the dough.
Okay, so you might go backtrack on that, because right now would only tell you that with this little sample, how they're oriented amongst each other, not that hay was pointing to the South Pole or North Pole or whatever. So y'all might go backtrack and see if that's what they really meant. Other questions?
Yeah. We'll clarify that going into the next semester.
So let me ask you, can you go back to your requirement slide, please?
This one?
Correct. You say you're meeting requirements. Through the meeting requirements, you have to verify and validate your requirements through testing. Have you done conceptual testing with CONOPS and Menteluminosa, verify and validate it?
We are still in the testing phase. We do have a couple of iterations of 3D printed boxes that we've gone through. There have been some issues with print quality, but as we get better at designing the actual box, we'll start eliminating some of the flaws we've been running into.
Any others? All right, thank you, team. All right, next up, from the University of Houston, clearly, we have the Astroneers. Lamar University, Astroneers.
Hey, good morning, everyone. Is this mic working? It's fine. You hear me fine? Yes, better. Okay, there we go. Hey, my name is Justin Ramirez. I'm an electrical engineering student at Lamar University. We're the Astroneers. I'll let a few of them introduce themselves.
My name is Prairie, and I'm also an electrical engineer from Lamar University.
Andrew Swindells. I'm also an electrical engineer from Lamar University.
I'm Mariah Rebo, and I'm also an electrical engineer at Lamar.
And I'm Francisco Barajas. I'm also an electrical engineer at Lamar University.
So our task and goal is to successfully lay fiber optic cable on the moon via a remote controlled rover. So we'll touch some of the aspects that we've designed so far and some of the flaws that we're dealing with now and some alternatives that we're looking at for the spring semester.
So like he said, we were tasked with developing a machine that could lay the fiber optic cable and power cables on the moon. So the way we attacked that task was by designing a rover that would be able to dig the trench, lay the cable, and then go back over it and bury the cable. When designing this, we took into consideration that the rover would have to withstand the conditions of the moon, such as the harsh temperatures as well as the rough terrain. But we also wanted to make sure that the rover would be reliable and require little to no maintenance, and if it did require maintenance, it would not be backbreaking, it would be easy to fix.
So some of the objectives that we're looking to perform are to, as Andrew said, successfully bury this cable. So what that entails is equipping our rover with a digging mechanism. Right now, we've kind of considered using a shoveling mechanism that could actually dig a trench. Free spinning spool mounted on the bottom, which is probably subject to friction or sticking, which is why we're considering maybe moving that in the future. And then a rear arm serving as a plow to successfully displace or move that displaced regolith back over the cable for protection purposes. So we're going to equip this motor with 6 12-volt motors, and each wheel will be independent of each other. So the front and rear wheel assemblies will be able to pivot 90 degrees, and the middle wheels will be stationary. The microcontroller we're looking to use is a Raspberry Pi or an Arduino with a Sierra Nevada wireless router for communication back and forth to the rover.
So some of the standards that we're looking for when it comes to some of the components as the communications receiver, we're looking at military standard 810G. Basically what the standard is that it will be able to withstand really harsh environments, as well as standard UL 6950. Basically what that standard is that the components inside of the communications receiver will be able to withstand high usage. And mainly our goal here with the communications receiver is to be able to use satellite data to be able to communicate and connect with the actual rover.
So yeah, 2 of the other standards that we plan on implementing here for our microcontroller, and as far as any other electronics or motor protection goes on our rover, these 2 standards that I have here listed pretty much ensure that the rover would be able to handle the, as Andrew mentioned, the cold nights on the moon, or as far as, during the day, it would be able to handle the radiation exposure from the sun.
So with that, like that. So with that, with the motors that we're going to mount, we obviously need to ground these motors. So we're following Article 250 out of the NAC code book to properly and ensure safe, reliable functionality for our DC motors and reliable function for our rover entirely.
So here we have some of our renders that we have so far for our rover design. As just mentioning, we have a 6x6 wheel design. We took inspiration for the wheel design from the Perseverance rover. Each one of these wheels will essentially be mounted with a motor, as Justin was mentioning. The two front will be moving, as well as the back, and the arch emitter will be stationary. Currently, our mounted spool, we have it mounted at the bottom of the rover, but after some feedback we received, we decided that it'd be better to implement this on the top. The reason for this, just for it'd be easier for the whoever's having to replace this spool won't have to ultimately flip the rover over to get the spool off. Having it on the top would be a lot better. And we also have a shovel as for our digging mechanism. As far as this, we're also looking for a new design because considering this shovel is going to be moving forward, and eventually some of that lunar sediment will carry over the shovel, essentially covering its own trench that it just dug. So we're looking into different designs for that as well. Lastly, we have our personal dirt drag that we kind of designed, similar to plow. This would just essentially get any lunar sediment and just put it back into the trench.
So for our need impact and constraints, we know that we need loader infrastructure development. This will help us establish a power and communication infrastructure, to support autonomous and manned operations on the moon. We also know that we need adaptation to lunar conditions. This is to engineer components to operate under low gravity, abrasive, rugged terrain, and also extreme temperatures. So the impact, we know this will support and sustain lunar operations, ensuring reliable connectivity and power distribution for moon communication. And some of the constraints we have is harsh environmental demands such as low gravity, extreme temperature, and also lunar dust. And another constraint we'll have is resources, and that can contain budget problems as well, and also manufacturing problems as far as getting our products to the moon.
So overall, our main goal here is to be able to contribute to be able to lay down cable on lunar base camps. So right now we are on the development stages and the conceptual stages. We appreciate everybody's feedback that has come to us, and we will definitely be implementing that into future changes for next semester. Overall, as of right now, for the communications aspect, we are thinking of using satellite for the connection as well as the microcontroller to be able to control all of the attachments. And overall, I would like to thank TSGC for the opportunity to be able to participate in this program, as well as everybody that has come over and talked to us and given us feedback. And with that, I open the floor to any questions. Thank you.
So if you've worked with electrical cable, especially like a cable that has a lot of insulation on it, it's very heavy, bulky, does not like to twist, or has a very specific twist that likes to stay, it has memory, it wants to stay in a certain position. And then when you think about all that being on the spool, also the spool is very heavy, bulky. And you're coming up with your concept, did you think about some of the mechanical force issues with just managing cable to begin with?
Yeah, so actually, as far as how heavy the spool would be, we've reached out to our mentor, and he's actually given us some insight on this. So as far as the spool itself, we don't have to worry too much of the weight, just considering the moon's gravity. So it wouldn't be as harsh for the rover itself. But we do plan on, later doing some FEE tests, just so we can kind of see how other joints and everything's impacted on the rover itself. We kind of haven't reached that stage yet, just because I guess the majority of us are electrical engineers, and it's kind of a learning process for us in the moment.
So you mentioned that the spool's heavy, and so it's on top that they're going to be doing this operation. How do you plan to get the spool to initially start to the process of spooling? Because I did not see the conceptual design showing how it plans to start. Number two, you guys have substantial amount of equipment on there. You're talking about a satellite that you want to put on there. You're going to need to be able to operate this mechanically on the motors on the wheels. You're talking about having a battery. You're kind of looking like a mini ROV instead of a little smaller robot you guys have. Because of that, yes, you do have minimal gravity on the moon. With all this weight, you're still going to weigh down and sink into the soil. Not soil, like rigor, but let's say it again, you're still going to sink down. You need to have stronger motors, stronger battery, more power. How do you plan to meet these requirements?
So the current design we have is that aluminum shell body. That would be our warm electronics box. So your first question was how would we expel that wire initially on top? We're considering mounting a motor, so it'd obviously be an additional motor. Keeping these small and maintaining weight is obviously probably our most subject matter. So that's going to be key when we start to fabricate our design. So motor assisted spool would probably be best for that application. And then your second question was about how will we, I guess, manage most of this weight. So I think we would use a similar approach as the Mars or the Viper rover that was canceled by NASA. So the aluminum, the sheet metal wheels that they use is probably what we'll go with for our wheel approach. And as far as the amount of equipment that we're going to use on this rover, I guess we'll kind of have to take those challenges as they come as far as weight mitigation.
Any other questions? I'm sorry, I lost focus. Can you go to the very beginning? Are you designing? You're not designing the comm system. They already told you it's going to be fiber optics or whatever. You're designing the digger. I'm going to use a different word there, Rover. Is that correct? Or what exactly was the task?
The task is to build a, like Robert had said, a robot or unmanned controlled vehicle that could expel fiber optic cable. So yes, the digging mechanism is a part of it. However, expelling the spool of wire is also the key factor.
That's what I'm saying. Be specific. They told you fiber optics, then you can focus on that. Right? Don't worry about wire or other things. Right? Worry about the properties of fiber optics and
exactly.
Does it coil and how much it weighs and all of that. So I just wanted to clarify that you're really working on the trench digger. Again, I'm avoiding the word rover because that's got other. You're really digging the trench and then burying the fiber optics cable. So
of course.
That's really the focus.
Okay. Thanks.
Any other questions? All right. Thank you, team.
All right, and now University of Houston Clear Lake and team the Backyardigans.
So good morning, everybody. We are the Backyardigans, a group of mechanical engineering students attending the University of Houston Clear Lake. I am Joseph Gibson, and I'm joined here today with Mr. Peter Bowling, Mr. Walter Sharp, and Mr. Matt Hello. And today we're going to be going over our Softgoods attachment device. So here's a brief outline of the presentation. I'm just going to cover everything that we're going over today and finish with our acknowledgements. So a little bit about the background here. Softgoods help provide thermal protection for sensitive equipment up on the ISS from solar radiation. So here's a picture. All these little white textiles on the outside are our Softgoods textiles. And those are the insulation, like I said, they're to protect any sensitive equipment. So astronauts essentially need a tool to secure soft goods to each other out in space. So here's a zoom in of the MLI, or multi-layer insulation. It essentially consists of 4 layers of mylar, or space blanket or emergency blanket, sandwiched between 2 layers of the X-Pack V21 material. So these are sewn together, and that creates one soft goods textile. So this is actually a picture of, if selected, where we'll be testing our project in the neutral buoyancy pool at NASA. So if we go ahead and imagine that everything in blue is insulation like the outside of the ISS, then here zoomed in, this blue dotted line in the center is essentially where an astronaut has gone in, cut out some insulation and, rather repaired or upgraded some of the hardware behind it, and they now need a way to basically put another flap on top to seal that hole. So right here, as you can see, there's an extra flap of MLI. We essentially need a way to only accessing one side, the front side of the panel, to connect that. So that's one of the biggest design challenges here. But to go more into those needs and constraints, you can go ahead and pass it on to Mr. Walker.
Thanks, Joseph. So now that he explained the scope of the project, I'm going to go over the product constraints that were laid out by the Micro-G design requirements for the project. So sharp edges must remain 3 inches away from handling points, and uncovered holes must be less than ½ inch or greater than 1½ inches in diameter. This is to avoid puncture and pinch points. Obviously, the EVA suits, it's critical that they're punctured in operation. Also, 3D printed parts must have at least a 75% infill, and the ultimate tensile strength must exceed a factor of safety of 2. It also, stress analysis should display a resistance to a 30-pound force pump load at any point of the tool. These are these constraints are designed to ensure that the tool is robust enough to operate reliably in harsh conditions. Some more constraints, it must weigh less than 10 pounds, preferably less than 5, and it must take up less than 1 cubic foot of space. This is obviously from a payload standpoint, that's important, as well as from a usability and ergonomic standpoint of the tool. The density must be greater than or equal to the density of water. This is for testing purposes. It needs to be neutrally buoyant or sink in the test pools. The linear actuation force should be less than 20 pound force, and the rotating actuation torque must be less than 30 inch-pounds. This is also from a usability standpoint for the astronaut in space who has limited finger mobility and force. This is our house of quality. On the left side, you can see these are our customer requirements laid out by the Micro-G competition. And then at the top, we have our selected engineering metrics at the bottom. You can see our units of measure for these engineering metrics and then our target values for each. A couple important notes on that house of quality is our safety. We are measuring that via the distance from sharps and the factor of safety for the ultimate tensile strength. We're also measuring if the actuation is being done by one hand by measuring the single variable actuation and how small the actuation force is. And then how intuitive the design is, we're considering how small the tool is, if it's a single tool actuation, and if it's easy to service and how fast the actuation time is. Also, we're measuring how reliable the attachment is via the connection diameter. And then I'm going to give it to Peter to talk about the concepts we discussed.
Thank you, Walker. For concept generation, we looked at several designs and methods of attachment already available in other sectors. Considering that the tool can only access the exterior side of the material, we narrowed our concepts down to a select 3. The first concept, based off a commercial blind rivet gun, involves punching a rivet through the material and deforming the rivet to secure it in place. The second concept, later realized to be similar to an automatic rebar tying tool, would drive a wire through the material with a curved guide leading around to the other side to secure it by a twisting of that wire. Our third concept is based off a commercial tagging gun, where you puncture the material with a hollow bore needle, allowing the user to drive one end of a tagging material through to the other side, leaving the other side of the tag on the original side, securing it in place. In evaluating these concepts, we settled on the following criteria listed here on this pew chart. From this, and considering the project's requirements and application environment, we put heavy emphasis on safety, ergonomics, and reliability. We then individually ranked these criteria, ranked the concepts, and took the average for each criteria, and resulting in the values you see here. This led us to ultimately pursue the stitch gun concept, but we have some notes for each. Concept 1 showed to be simple and safe, but heavy and required more force to actuate. Concept 2 was safe, but complex and cumbersome, leading to more potential points of failure. Concept 3 was simple and effective, but potentially less safe with the exposed needle on the end. But there's ways to mitigate that, such as a retractable sleeve or a removable cap. With our final concept selected, we moved on to modeling and analysis. Our concept is divided into 3 separate sections. The first section is the housing, which houses all the internal components and secures them in place. Then we have the trigger mechanism pictured on the left here, decomposed, and the punching or tagging mechanism pictured in the middle. These 2 systems are linked by the primary lever arm and the primary slider, labeled as part number 4 and 5. I'll go ahead and pass it back to Joseph to go over the preliminary analysis.
Thank you, Peter. So quick comment before I get into it was that the main stress analysis, including FEA or finite element analysis, as well as more material selection will come next semester whenever we do our prototype, as well as all the testing that comes with it. But for these calculations, we went ahead and used tough PLA for materials, since this was on NASA's approved guidelines of materials. And we went ahead and just calculated simple stress at the weakest point, or essentially where the material, where there's the least amount of material. So doing that, we knew that it's required to withstand a 30-pound bump force. And we did our calculation to show that it passes the stress analysis with a safety factor of 9.5, where we only needed to pass really 2. So with that, we'll go ahead and pass it on to Matt to go over our project work plan.
I think Joseph, though, as you can see that in the project work plan, though, we created a work breakdown structure, though, just to outline a task and a subtask, like you see on the right side with on the section, and the next slide. And the next slide, with a full section, though, we created a task responsibility matrix by using a work breakdown structure just to assign ourselves for this semester, though. Within a assuming, though, you see like 2% who's doing either P as a primary or S as a secondary, though. Finally, and again, Jordan, you see this section we set a deadline just to compete with that 8 time limit for this semester. It would be for the noise of for the next semester once we on the next phase. And to get a better closure how it is, you see how we have like the date specifically that we need just to complete with it. And just I pass it back to Joseph just to reach the conclusion for this project.
Thank you, Matt. So in total, the Softgoods attachment box is reliable and ergonomic, and will be easy to use and create a strong connection. We chose to really focus on ergonomics as well as ease of use. It has a very low actuation force as well as a low actuation time. With the coming semester, the team looks forward to creating the first prototype. So this includes actually making the NASA tag gun as well as doing all the testing that comes with it, ensuring that it'll be able to perform pretty reliably, just over and over quickly. With that, we'd like to give a few special acknowledgments to the TSGC for even giving us the opportunity to do this project, as well as our mentor, Dr. Yusuf Hamidi, for helping us throughout the semester. With that, if anyone has any questions, we'd be happy to answer them. Thank you.
Questions for the team?
Don't get shy for us.
You can probably, yeah.
So you talked about requiring more pressure to, I guess, get through the fabric.
is that a concern with pushing the gun against the fabric, maybe damaging it?
So the main thing about the stress analysis, like the constraints that it needed to withstand the bump load, and I think that's specifically referring to like dropping the tool or bumping into things. There's also, if you're talking about the linear actuation force, we're actually talking about like the actuation of the tool itself. But the stress analysis should just show that it can withstand a 30, all it said was 30-pound force bump load. So that's really all we're considering. But looks like the material properties aren't going to be like the main issue of the tool. The main testing of the tool, like whether it can complete its designated function repeatably, is going to be like the cohesion of like the small parts within the tool, and that's going to have to be tested after build. But material properties so far not looking like an issue. Like you said, we had a 9.5 safety factor.
Other questions?
Thanks, guys.
Thank you. All right, that ends our second session of the morning. We're going to take a break until 10:55. session. All right, welcome back. Everyone can take your seats, please. Please welcome from San Jacinto College, Team 13 characters.
Hello, we are 13 characters. I am Jonah Davies, the team lead.
I'm Natalia Gomez, the co-lead.
I'm Giovanni Trujillo, I'm the team member.
I'm Andrew Mediola, I'm a team member.
The goal of this design challenge is to build an ICR, incapacitated crew rescue craft, for crew members who are injured on lunar EVAs. The function of our design will be a cart that the crew will bring along with them during these EVAs, so that in the event that one of them is injured, they do not have to head back to base and get it, and they can just pack them up and go. The frame of the design will be 6 feet by 4 feet by 4 inches. It will be an aluminum truss using the alloy 2219 for its temperature and structure performance. Beneath where the incapacitated crew member will rest, there will be a lattice so that they are supported and do not just fall through the truss. The frame will have 4 primary attachments, the first of which will be a seat bagging, which will be mounted on the frame facing backwards for them to rest on. There will be a cavity within it for their life pack to basically sit in so that they are not just floating there. There will be 4 storage compartments on the frame. There will be 2 smaller ones, 2 larger ones. There will be 2 on either side. There will be a ramp stored within the craft that is roughly 5.5 feet long, so it is as long as possible, making the angle of it very shallow to assist with lifting crew members or heavier samples onto the craft. And lastly, there will be a harness at the front of the craft, which the driving crew member will hook themselves up to, which will allow them to steer the craft and move it with ease. In the event that a crew member is incapacitated and injured, the car will be maneuvered toward the rear is facing them, the ramp will be lowered down, and then a winch will be connected to the crew member on 2 shoulder hooks, and then they will be lifted in using the winch, which will have 2 handlebars to allow them to easily be lifted. Once they've been lifted up, the hooks will be detached and their pack will be set within the cavity in the seat to hold them in place, and then a set of dual retractor seatbelts will be used to additionally support the crew member and keep them in that position so they do not bounce around during movement and do not float off. All right, and now it's Giovanni.
Yeah, let's switch sides.
I did not move it.
Just adjust this here? Okay. As Jonah described, there will be multiple attachments to this craft. 3 of these will be very crucial: the seat, the ramp, and the winch. I'm going to talk about 2 of them simultaneously. The ramp, it will be stored underneath the craft. You pull it out, and it will be at a shallow angle, so the person that's going upwards will not be uncomfortable. And to bring them up, there will be a winch behind the seat that you pull out and attach to the shoulders of the person, the incapacitated crew member's suit. And to power the person going up, it will be dual anchored by the person rescuing them. And after the incapacitated crew member is brought up to the seat, they can be attached using a seatbelt over their shoulders, and it will be clamped down by their legs. And then after that, we also have storage compartments for these. The two of them, two big ones and two small ones. All four of these will be open from the top or open from like drawers. And in case of an emergency to rescue someone, they can also be detached, so there will be less weight on the person rescuing the other crew member.
Okay. So the harness would have size and attachment points, which would be at the waist, and there would be an upward incline on the harness to be able to go over the stomach and sit comfortably on the crew member. So there's some wiggle room, so it could be like I think 15 degrees above, just in case that the person is a little taller than the average person or shorter than the average person. I'm so sorry. Okay. The harness allows people to steer the cart through an L-shaped bar that would go underneath the cart and would be attached to wheels. So if the person who is controlling the cart would turn left, the cart itself would turn left, and if it was turned right, the cart itself would turn right. Along with that, the harness would also be attached to the cart with bars on the side, just to make sure that the person's stable. And if the person was to fall down or anything, the harness would be able to detect that and stop the cart in case so no disasters happen.
I will be talking about the brakes. I'll be talking about the brakes and the wheels. So the brakes, we decided to go with mechanical brakes that are similar to bike brakes, where they're connected by a wire. So the more you pull, the more force is applied. So you can have kind of a slow deceleration of the cart instead of an instant deceleration. So to kind of keep the crewmate as comfortable as possible. So instead of it being a sudden stop and jostling the crewmate around and further injuring them, it brings them to a slower stop. It will safer for the crewmate, more comfortable. The wheels themselves, we're going with 2-foot diameter wheels with 8-inch diagonal lattice treads, and the fenders will have fenders and flaps to prevent buildup of lunar dust on the wheels so that they spin fine. And we're also going with a dual wishbone design of suspension for better comfortability and performance of the car. And the only drawback of the dual wishbone design is that it's much heavier. We also have is it here? Yeah. We're also gonna go with a dual motor design for the cart so that to make the initial movement of the cart much easier on the crewmate, so that as minimal effort as possible to move the cart with high torque motors that activate to make it easier to move the cart in its initial movement, and then switch to lower torque gear for the continuous movement of the cart.
I would like to thank our professor and Vaughn for helping us with this design project, and the TSGC team for allowing us to partake in this. Thank you.
Any questions?
Questions? I'll ask one. So what was the most challenging part so far on this project? You can't say everything.
Choosing which things to keep. Probably the stripping down of the initial 2 designs we had and then combining them into the final one, which we are currently using. The first half of the project was us splitting up the team into two groups, one for a complex design that would be reliant on electronic systems and have a lot more functionality, and then a secondary design that's main goal was just to rescue the crew. It would be simple, it would be light, and it would just amount to a mule cart with wheels and just on the moon.
Other questions?
I was gonna ask, what does your stove configuration look like?
Or what configuration?
Like stove, I assume that this somehow gets deployed into its transportable configuration.
That is something we will be designing in the second semester. We have not done that yet because we've been focusing on the primary functions of craft and the other parts of it, such as the wheels, electronics, brakes, other things like that.
And then my second question, just like with the other team, what do you anticipate the total mass of your cart to be?
At a guess, I would say probably about 120 kilos on Earth. On the moon, that would roughly translate to about 20 kilograms.
All right, thank you, team.
Sweet. Ooh, that's really nice.
All right, so please welcome Houston Community College and Team NED, Nuclear Engineering Dynamics.
Good morning, everybody. How are we? Are we doing good? Belly's full. We have energy, attention. Belly ready for this? Okay. We are Nuclear Eagle Dynamics with Houston Community College. My name is Jessica Tidwell. I am the team lead on this project. And next we have
My name is Johan. I'm a team member.
My name is Sam Davis. I'm also a team member.
My name is Derek Bukowski. I'm also a team member.
My name is Karim Marodi, and I am a team member.
Hello, everyone. My name is Camila. So let's talk about our project. NASA launched the Fission Surface Power Project, and the goal is to bring the human's presence to the moon and to provide the power for the Artemis 3 mission. The challenges that we're going to meet when we go to the south pole of the moon, we're going to talk about our location a little bit later, but I'm going to talk about the challenges. The challenges are, the first thing is that there is 14-day light cycle. That means that there's 14 days of light and it changes to the 14 days of darkness. The other problem is that the surface of the crater, it has the temperature of the crater, it changes drastically throughout those 14 days changes. I'm so sorry. It's just a little bit, yeah. But anyways, so these are challenges, and that is why we did not go with the solar power or fuel cells. That's why we chose the nuclear power reactors. Our reactor is going to provide big amount of power, and it's going to withstand extreme conditions on the moon. The goal is to bring the CONOPS to NASA so they can build their framework based on our CONOP for the future fission surface power project. So the nuclear reactor that we're going with is made by X Energy, and it is XE100.
So this is our beautiful baby. It's the XC100 by X Energy, as she said. So we chose this reactor based on two things. It's design philosophy and also its safety features. It is a small modular reactor, specifically a high temperature gas reactor. Sorry. It is capable of producing a 200 megawatts of thermal output. It has a 45% efficiency rate, which means that its electricity potential it's estimated to be 80 megawatts. Okay, so I think that's pretty cool. Okay, but, and it also has like a 6-year lifespan, which surpasses the requirements for Astro. Its design philosophy is meant to be like so it's meant to improve the economy by simplifying the system, as well as reducing the time in construction and infrastructure, and as well as simplifying this like modular components. So the safety features, one of them is that it's intrinsically safe. As you can see here, it has low power density of 4.8 megawatts per square cube. Its engineered safety systems are meant to be passive, so if any spurious signal is sent to the reactor control shutdown system, this will just cause like a minor increase in temperature and will cause no damage to the fuel. Okay, it also has a decay heat removal in the safety features. The way it works is that heat removal it passively decays, so the fuel temperature will remain in the safe limits. As part of the containment function, in case of failure, the building that releases helium through the filter vents to reduce the radioactivity. Yeah.
So our XC100 reactor will be powered by TRISO fuel, and what TRISO fuel is tri-structural isotropic fuel. It has been tried and tested and improved for the past 60 years, so it already has lots of records and obviously improvements. And so what it is a billiards ball size pellet filled with 18,000 particles of uranium oxycarbide. And outside those 18,000 particles, there's 3 layers of carbon and silicon to coat it. And through our XC100 reactor, there'll be 220,000 of these little billiard ball pebbles, which will be gravity fed through our fuel handling system. And the way our fuel handling system works is a 4-component system, which will account for 100% of the fuel movement because it's a closed system. Nothing will get out. And through the system, it'll be all the fuel pellets will be removed once they're done, and then replaced by new unused fuel pellets on a daily basis. And another feature is that there's a sensor or measurements that will measure how much fuel is left from the fuel that's taken out, and if there's still fuel left, we can recycle it back to the system, and it can be used again and again until every fuel is taken care of. Adding on to the safety features, as I previously mentioned, these TRISO fuel pebbles, every single one of them is coated with 3 layers of carbon and silicon. And what these do is they contain a majority of the gamma radiation and other radioactive materials. So everything is contained with minor risk of leak. And with our reactor, we plan to send it up to the moon with our via the Falcon Heavy rocket by SpaceX, and this will be launched by the Kennedy Space Center. We chose Falcon Heavy over other rockets because
It's because due to the renewable rockets or renewable boosters design, it adds for cheaper costs and a higher payload capacity. And once our rocket is sent up to the moon, we will land it inside the Shackleton crater, which is located near the south pole of the moon.
All right, so the way we are going to get XC100 to the moon is through Falcon Heavy. Falcon Heavy has a very high payload capacity. We have a very big reactor. It's a small modular reactor, but it's bigger than the majority of the ones being conceived to go to the moon. And the reason we chose that is because NASA wants a 10-year operating life. We're giving them 60. We're giving them 60, and we can send them more reactors if they want more power. So our objective is to transport the XC100 reactor, the TRISO fuel, and the steam generator. They will most likely have to be separated into different rockets. We are going to land them directly into the crater. It's easier to transport that way. We don't have to make an entire plan to land it outside of the crater and then move it down into the crater to get it to its location and then assemble it and then get it running. Just let's land it there, let's assemble it, and let's get it going. Let's get some power running. Once we land in the crater, we'll establish and integrate systems to make sure that it's up and running. And once it's running, we plan to launch a second reactor. So this is the Shackleton crater. It is roughly the size of the inner loop of Houston, the 610 loop. It's about 21 kilometers in diameter, so it's pretty big. It's also about 4.2 kilometers in depth. If you look at the bottom left side, you can kind of see a comparison of a cross-section of it, what it would look like if you were inside the crater. The reason why we're going with this is because NASA has already decided this is mainly the spot we want to extract resources from. And because of that, it's close to the connecting bridge of the Hinson crater, which is to the southwest. And then it also has the Spudis crater to the northwest, I'm sorry. So with that, we will give you more details on the Shackleton crater.
All right, so I'm gonna first start by saying we need a crater specifically for this because it shields from a lot of radiation that's on the moon's surface. So there's no ozone layer around the moon, so there's a lot of radiation that goes through the moon's surface. And up here, you're gonna see the little pink square. That is where we decided to land our crew. We do not want to land our crew inside the crater because that is where our reactors will be. And the stars will be potential locations for the base. Now, the reason we chose the Shackleton crater in particular is because it's located on the south pole of the moon, and it is close in proximity to a lot of resources that NASA and the government want to mine for on the moon, such as water ice and rare earth elements, such as iron and helium-3 isotopes. Okay. So on the screen, you'll see the first photo is 6 pictures throughout a 14-day light cycle on the south pole of the moon. And the second image is 14 days of the dark cycle. So the reason we decided to put the reactor inside of the crater is because if you'll see, the blue spots are about -240 degrees Celsius, and the red spots are anywhere between 130 degrees Celsius and 70 degrees Celsius. So the red temperatures on the outside of the crater can fluctuate almost 300 degrees Celsius, which is why we decided to put the reactor inside the crater so we don't have to worry about that fluctuating change in temperature.
So when it comes to our power distribution plan and our plan for power on the moon, we took in consideration that we want this to be the base for the infrastructure of the power on the moon. So we went with a 2-reactor setup, not only for it to be the base for future expansion and upgradability, but also for safety. In case one fails, the other will pick up. We also have 2 separate
power lines connecting to the microgrid controller and the undisturbed power supply station. We picked the undisturbed power supply solution for two reasons, which is first to supply consistent and stable power output to all the mission's needs. And the second is, in case of a failure, you have the batteries to sustain the human life over there. Also, our reactor is inputting 80 megawatts of power, and our estimates say that all we need is about 200 kilowatts. All the components will be rad hard to further prevent any effects by radioactivity. And we really see that this can be upgraded in the next phase to a 320 megawatts solution to further expand our power on the moon. When it comes to evacuation, we really care about our astronauts. In case of anything happening, even though this is a very small percentage, we plan to transfer all the crew through a lunar training vehicle all the way to the Spuds Shackleton, to the Spuds crater. Over there, they can stay until any kind of danger gets away. We have sensors to sense that. In the case of extreme danger, they can go from there all the way to the lunar gateway, and from the lunar gateway, they can see if they can go back to the moon or go back to the Earth.
So, what's next for us? We have a lot more we want to discover about this reactor specifically and the things it can provide for future exploration, and that expands us into Mars. We have poured our hearts and souls into this, and we really believe that this reactor is the solution for NASA. So with that, we had some constraints with finding out information because a lot of it's proprietary. So you can ask ChatGPT, but it doesn't have answers for you. So we want to get the specifications of the payload for transportation, specifically how we will load it and unload it. We would like to make a video on that process. We also want to establish operations for the assembly of the reactor. So how would they assemble it once they get it out of the rocket? Another thing is we want to define some parameters around the radiation exposure. So we say if the radiation gets too high, we want to move them to Spuds crater, right? But what is too high on the moon? Because there's constant radiation on the moon due to no atmosphere. So, and then aside from that, we're just going to champion ourselves to push towards Mars as well, because this is one very incredible reactor. And with that, thank you. We want to give a special thanks to Tim Urban, Robert Knuckles, our NASA mentor, and our faculty advisor, Topa Sapalucio, who could not be here today. If y'all have any questions, please let me know.
All right, thank you, team. I think we're out of time completely now, but you'll be here later.
Yeah, if you have any questions, you can let us know and answer them after the whole stage. Thank you.
Next up, Team Menteluminosa from University of Houston, Clear Lake.
Hi, good morning. My name is John Klonch. I'm joined with Adam Kennedy, Andrew Klein, and Sophia McNogia. And we are Team Menteluminosa of University of Houston Clear Lake. Today we're going to talk to you about our lunar contact sampling device. So first off, give a little outline of kind of what we're going to do. We're going to start with the background, go through the criteria and constraints of what really drove the design and what kind of conceptual designs we came up with based off of those constraints. Then go into the modeling and the dimensions of our proposed idea and then our final idea, and then go through some technical content that we did and then wrap it up with a conclusion. So first off, we're going to go over the background. So what's the goal? What's the point of the project? So the point of the project is to design a lunar contact sampling device that can tape a sample of the top 1 to 5 millimeters of lunar regolith on the top surface of the moon. It needs to be operated by an astronaut in a full EVA suit, and it needs to meet the standards of the NBL and the SDL labs at JSC. And so one of those things we collect is through the Micro-G competition. So we took all of the design constraints provided by the Micro-G competition, and we developed them and put them in 3 kind of categories that they gave to us. So the first one is functional criteria. So basically these are criteria that are designed for actual use of the device. And so one of the big ones are it needs to be less than 10 pounds. It needs to fit in a mass of 8 by 8 by 36, and it needs to be completely mechanically operated. The second is material constraints provided by the Micro-G competition, and then safety criteria. So how will the device actually work around, and will it harm the astronaut in any way? And so we took all of those and we built an HOQ, and we built it around some engineering requirements, and we kind of fed this through to really build our concept generation process. And so now I'll hand it off to Adam to go over the concept generation.
Thank you. All right, so for our general concept, we broke our design into 3 main components: the handle, the shaft, and the collector. We decided early on between doing a modular design or a non-modular design. We picked modular because we can, if anything is wrong with one specific component, we can fix that component without having to completely change the entire design. Some early brainstorming sketches we did is for each of the 3 components, we did multiple different design concepts for them. Some is for the shaft. It was mostly having it collapse in on itself or fold so that it can meet the minimum storage requirements. For the collector, it was the different ways that we can collect the sample with preserving grain orientation, getting that 1 to 5 millimeters. And for the handle, it was how the astronaut's gloves would mostly fit and how he could operate it effectively without problem. Here are some early CAD models for some of our runner-up concepts. These were mostly handles and one collector, a side grip handle for operating when the collector would open and close, a top one for carrying, and a kind of dustpan-like collector that was not used. Moving on, we did our decision matrix for each of the 3 different concepts. For the scoopers, for a collector or scooper, we picked a rotating kind of hole punch type design. For the shaft, we picked a modular screw-on of different pieces. And for the handle, we picked a bicycle or scooter-like handle with 2-handed grip at the top. I'll now pass it on to Andrew for our concept, final design.
Thank you. So as Adam previously stated, these were the final concepts that we designed, and we took our modular approach and then evaluated each one. So we have our handle, our actual sampling device, and then our shaft. We went with threading to attach each device to each other because it's easy to use and most everybody understands it. Here we can see the device assembled together. The dimensions of this, we have a mass of 4.78 pounds. We have center mass dimensions there. The material we chose is 6061 aluminum. This is because we have weight requirements as well as a safety factor that we need to meet, and we found that aluminum meets these requirements very well. The total height of the device is around 40 inches. However, this can be adjusted because of our threaded shaft pieces. We can add more or less depending on the height of the astronaut or the user. The handle length is the length from tip to tip of the handle, and that's about 14 inches, as well as the bottom sampling device. Bottom diameter of the sampling device is around 6 inches in length. So how does this device work? Well, think of like a salt shaker or a pepper shaker. There's a twisting knob on the top. So when you want to take a sample, you'll twist it to open,
push it down onto the lunar surface, and then twist it again and close. One design criteria that our team outlined for ourselves that wasn't in the micro-G competition, we wanted to be able to take multiple samples at different parts of the lunar surface without having to get another device. So here you can see the device in motion. There's a handle brake on the handle that attaches down into the device that will be connected by a wire and tension. When the handle bar is pulled, it will cause a spring to compress, and the device can then be rotated. As you can see here, we have the device rotating between an open hole and a closed hole, and this allows the sample to be observed. I will now turn it over to Sophia to discuss our technical comment.
So we decided to initiate or commence our technical analysis by determining the spring constant. One important thing why we decided to start off with this is this would help us in coming up with a set of parameters in order to design the spring, because as mentioned by Andrew, there are two sets of springs that will be used in the prototype. So if we don't know the appropriate parameters that will be needed for the spring, it might result in any failure or maybe permanent deformation. So we use basic mechanics concept in order to identify the spring constant, which at max was 306 pound force per inches. The F max is technically the maximum force that will be exerted by the astronaut in applying the brake. We then moved on to run a performance characteristic test using stress analysis. Our basic concept that we used in this case was distortion energy theory. We needed to see how these stresses would be developed when force will be applied on the handle, which in this case, the maximum force requirement was 20 pounds force and the maximum torque was 30 pound force inches. So at a maximum of 20 pound force, we have a stress developing at a bending stress at 2.2 kilopascals force per inches, and maximum moment that was developed due to torsion was 82 pounds force per inches. After using the distortion energy, our safety factor was at 18.2, which was quite high than the required, which gave us a little faith in our design. And future endeavors on this would include conducting a few analysis once we venture into the manufacturing stage. So on wrapping everything up, we'd like to extend our heartfelt appreciation to TSG, to Micro-G, and to our instructor, Dr. Miller. Also, just a brief introduction of future endeavors, we'd like to, as I mentioned before, we'll be conducting a few analysis while the prototype is in the manufacturing stage. That will help us decide what are the design machine elements will be needed in order to assemble the device. Thank you.
Questions from the team?
Can you go back one slide, please? Sorry if I missed it, but are the handles, are those hollow or are they solid?
We're planning on making them hollow to reduce weight. However, if needed, they could be solid. This analysis was conducted on hollow handles.
Okay. Are there any thoughts to, since the fact that the is so high, are you guys planning on reducing the size of it or the thickness of the handles, or are you sticking to that thickness just for like dexterity reasons?
It's a possibility. We could change the material or make it lighter if we wish. However, we're well below the weight requirements already, and we'd like a rigid and stiff handle anyway for operation ease.
Thank you.
Other questions?
So I wanted to ask, what is the sample size?
Currently, our sample size, the bottom radius of the circle that collects the device is 1 inch across. So we have a surface area right now that we're collecting of pi, which is 3.14 square inches. We're currently modeling another design for the bottom. You can see here, that's a little bit of a different shape. So we'll be able to collect 2 samples of 9 square inches as opposed to 3 samples of 3 square inches. So we're looking at exploring some options there.
Thank you.
Any other questions? All right, thank you, team. RELLIS Rovers.
Okay, good morning. Thank you for being with us today. We are the RELLIS Rovers from Tarleton State University, presenting you our designs for our lunar personal electric vehicle. Meet the team. We have 4 mechanical engineers with 3 seniors and 1 junior. We have our faculty advisor, Dr. Sharifi, here from College University. We have Scott Askey all the way at the back from NASA. We also have Chapman Lansdowne. He could not be here, unfortunately, today. The agenda for today will be going over the background, previous design, current design, testing results, future considerations, and then we'll end it with conclusion and question answer. Easton will talk more about the background.
Thank you, Akash. Today I'd like to discuss our project. I'd like to introduce the LPEV. It is the Lunar Personal Electric Vehicle. Some unique challenges that we're going to face for this project is the rugged and abusive terrain of the moon, the size, weight, and power, and the cost of sending materials to the moon, and the astronauts' lack of mobility. Some constraints that we decided to keep in mind for our project is to keep out the lunar dust from inside our wheels, to protect the motor from damage, the portability, safety, and range for our LPEV, the availability to traverse the terrain, the suit's mobility, and a safe speed for the passenger on board. Some foundational research that we conducted is that the lunar gravity is 1/6 of Earth's gravity. Another one is the lunar surface is much different than Earth's surface anywhere we can find. It presents the challenges of traction and regular penetration. So we decided on a 2-wheel stand-on scooter-based concept for our LPEV. We designed a Q chart to test 5 different concepts for what we can choose and the different criteria we're going to test them on and give them a score based off those. These criteria is stability, size, portability, safety, and ergonomics. From this Q chart, we were able to tell that the 2-wheel stand-on scooter was our best option for our project. And as you can see, this is our current scooter design. It is a skeletonized 2-wheel based concept with a folding capability for allowing easier transportation. And this is our current wheel hub that we have. It is made of 4 different parts: the outer wheel cap, the outer wheel, the inner wheel cover, and the motor hub. Now I'd like to send it off to Sway so we can talk about the previous wheel design.
Good morning, everyone. So this first design is going to be the original concept from last semester. As you can see, it's just a straight wire design. The pros of this design is it's very lightweight, it's very simple and easy to manufacture. The cons is once we actually performed FAA analysis on this wheel, the forces required for the scooter, it did fail. The next con is going to be that due to the space between the wires, it does allow for foreign object penetration, such as rocks, which will lead to wear and failure on the inside of the wheel. This semester, the first new design is going to be the straight bench design. The pros of this one is it is very lightweight and it does not seem to bog down into that lunar regolith. The cons for this one, it also failed the FAA analysis due to the cross-sectional area of the wire, which is too thin. The second con is going to be that once we did physical testing, we noticed that this wheel likes to retain a lot of that lunar regolith inside of the wheel. And another con is that it had very low traction relative to the other wheels. Our second new design is going to be the cross-wire design. This design is also very lightweight. It's a simple design. Passed our FEA analysis and had acceptable traction in our physical testing. The one con that we thought of is that due to our design having a stacked wire design, once we introduce lunar regolith, there could be potential wear on the wires leading to failure. The last wheel design is our honeycomb mesh. Unfortunately, due to time constraints, and as you can see from the cons, it's a very complex design. We were unable to physically test this design. From the FEA analysis, this is a very strong wheel. There's the least amount of deformation, which could be a good or bad thing, depending on physical testing. Another pro that we're looking forward to is potential traction with this wheel compared to the straight mesh design. The other con is that this is much heavier than the other wheels we're considering. So as you see, these are all of our 3 new designs side by side. And then to discuss physical testing, I'll give this to Silas.
Thank you, Slade. All right, so this year as a team, we decided it was absolutely imperative that we build real prototypes and do some actual testing. You know, we believe that you can do fancy simulations all day long, but at the end of the day, you need some real testing to get some real proof of concepts. In order to do that, we built our test bed here on the left. It's composed of 2 major pieces. You have the frame and the actual test box itself. The frame is an aluminum frame with a low friction bar that can slide from end to end. And attached to that bar is a free-floating wheel arm. On the bottom of that wheel arm, you have a motor holder, the motor, our keyway axle, and the wheels themselves. Those wheels can be quick swapped for easy testing. And then on the back of the frame, we have a force gauge with which to test the force required to overcome static friction on the wheel. The test box itself, as you guys know, the lunar surface is very difficult to deal with. It's like a fine powder and it likes to cake and build up. So in order to simulate that, we use quickcrete mortar mix, which closely resembles the lunar surface. It's the best thing we could acquire with our needs. So this is our first test here. This is a solid browser wheel. We wanted to use this as a good baseline with which to compare other mesh and wire wheels to. And as you can see, that lunar simulant really likes to build up on the browsers. This thing just turns into a ball and seats under its own weight every single time we test it in a fit. Second test is our mesh wheel. You can see it's very lightweight, but because of the straight mesh, it has no bite. It doesn't really want to grip the lunar surface to give it any kind of traction. It really just spins on the surface and collects that simulant. Next is our crosswire design. Unlike the mesh, this wire will actually bury into the ground, giving a really good bite, really good traction. And because it's so porous, it'll leave all that lunar simulant behind. Here's a good video of all 3 wheels going at the same time. Next is some actual data. So all the data points you're going to see going forward are averages based on multiple tests. Our first data is friction force. This is the force required to overcome static friction of each wheel. You can see that crosswire wheel there sits in a really good happy medium. We're really proud of that. Time to complete course. This was a good just overall test metric for us of just how well it performs overall. You can see the solid wheel fails completely, whereas the crosswire wheel was our fastest. And then how much each wheel saved. This is really important to us because we don't want our scooter to get bogged down and bury itself. So you see the solid wheel buried itself completely, whereas the cross wheel buried itself more than the mesh, but we wanted that for good traction. So we had plenty of testing errors. You know, we did a lot of testing. There's a lot of things to be fixed, right? So first off, that inconsistent wheel arm angle, that free-floating wheel arm I mentioned earlier has a tendency to sway from side to side, gives uneven contact with the wheel to surface. We really want to mitigate that for the future. As for the apparatus rail friction, it is low friction, but it's not frictionless. There is some friction going from piece to piece. We would really like to smooth that out as much as possible for next semester. Inconsistent power feed to wheel. I know a lot of you guys came by our booth last night. We actually were able to give you a wheel demonstration. You do turn the wheel physically. We are human and cannot give a consistent time for a turn every single time. We would really like to mitigate that next semester. Inconsistent density for mortar mix. We do our best to fluff the mortar mix every time before testing to make it the same every time. We do not currently have a way to measure that density. We are hoping to get that for next semester. And then non-ideal wheel assembly and materials. Our prototype wheels are very much prototypes. They have rough edges, and the materials are what we were able to source quickly, and with our financial means, we're hoping to get nicer wheels for next semester. And for future considerations, we would really like to implement a new motor design, hopefully like a bicycle chain system to make it really smooth. We would love a bigger test bed and bigger wheels. Implementation of slopes and testing and implementation of obstacles that was emphasized by our NASA mentors. That's really important. It will 100% be in the testing semester. We would love a prototype honeycomb. And we did get some feedback last afternoon about stability of the scooter. And it was suggested to switch to a 3-wheel design. We will be considering that in the future. So in conclusion, our crosswire design is the current favorite. It performed really well. We do need new testing scenarios. We do need to refine our testing system to make it consistent. And we would really like a prototype honeycomb next semester. I'm going to go ahead and pass things off to Akash to finish this up. Thank you, Cyrus. So we did take a look at some NASA standards. We took a look at the factor of safety. Our hub came to about a 2.3 factor of safety, so it is better than what's used on Earth currently. We also took a look at the design standards. We'd like to acknowledge NASA and TSGC, especially Dr. Urban, for letting us come out here and showing you all our designs. And also a quick shout out to Mayfield College of Engineering from Conceptual University. And at this point, I'd like to open up for questions. Thank you.
All right, so here's the question. So on a vehicle, even a car today, the most important creature of the car is the wheels and then the brakes. Because if that doesn't work, you're in trouble. So have you looked at forward motion for these wheels, but what about stopping capability? Have you looked at how well these wheels can facilitate stop?
So that is one of the future considerations. This semester, we mostly worked on just the wheel designs because that's 60% of the design. If there's no wheel, obviously the scooter is not going to go anywhere. But we do know that we cannot use braking because if you brake the scooter, it's just sort of going to slide. But that's one of the future considerations to actually implement some sort of braking.
So when you went to looking into the testing, they did not see any testing of load application. So when you go into looking at load application, different astronauts weigh different weights. You also have to understand collection of material, but also when you have this system, you're going to need to look at lighting that you'll need on this. So they're going in different directions, therefore you're adding weight there. In your testing results, we did not see any of that. Please tell.
Yes, sure. So for physical testing, it was originally planned to include testing under load. We unfortunately did not get to that testing. This semester, we are kind of relying on that FEA testing. So the FEA is about 319 newtons applied to the contact surface of the wheel. So up until this point, that is the most recent data we have on any type of load on the wheel.
Is that FEA test done on lunar surface gravity, or are you using Earth gravity on that test?
Yes, sir. So that is going to be the 1/6 of Earth's gravity or the lunar gravity.
I like the presentation. Did y'all consider using like fins or something instead of wire that would like maybe increase the surface area normal to the force that's going to be like acting to repel the vehicle, or maybe like a scooping motion? I mean, like I didn't know the logistics, but I was wondering if y'all thought about it.
Bear with me 1 second.
Like similar like paddles on like the
Okay, so that's what the fins you're talking about, I'm guessing?
So like instead of the wire, it would just be like sheet metal like cut out. Almost is what I was imagining. So you'd still have like it would still be hollow like your crosswire design, but instead of like round wire, it would be like flat fins.
Oh, I see what you're talking about. So that's going to be harder to implement, especially when we put it on your scooter, because the scooter mechanism is going to go on top of the wheel rather than currently it's on the sides of the rovers. So it's definitely something we can consider, but as of right now, these are the tests and designs we came up with, but that's a good suggestion for next semester.
All right, thank you, team. All right, that concludes our morning. Let's give everyone presenting another round of applause. All right, so it's just about lunchtime. So lunch is in the Hotel Paradise Reef restaurant. So you want to go across the breezeway into the main building, all the way down the hall back to the lobby, and then loop back around to the restaurant. We're going to take about an hour for that, and then teams, when you come back, go back to your posters for about half an hour. Few teams have not finished judging each other, so finish that up at that break. Also, our NASA folks that are judging will be around probably at that time too. And teams that are presenting this afternoon, if you could get me your presentations either right now